This is part 4 of chapter 8. In this video, we're going to be talking about the stereochemistry of substitution reactions. So as you can see here, the outcome of the SN2 reaction actually has an inversion of stereochemistry. So this is actually why we care about the mechanism, whether or not it's SN1 or SN2. Because of the way the SN2 works, we get a complete inversion at the stereocenter. Whereas in the SN1 reaction, which you can see down here, you're getting a scrambling of stereochemistry, or you can also say that we're seeing a mixture of two products here. In this case, we're getting a pair of enantiomers, whereas in the top case, we're getting one clean product. So what you can see is that the inversion of stereochemistry occurs because of the way the nucleophile attacks in the SN2 reaction. In the SN1 reaction, we have a heterolysis or a heterolytic cleavage as step 1, and so that carbocation intermediate can allow the nucleophile to approach from either side because it really doesn't have any shape to it. So as I mentioned in the SN1 reaction, once you form the carbocation intermediate, and that's shown here, the nucleophile can attack from either the top or the bottom face because the carbocation is going to be flat. So there's no stereochemistry associated with it. So if you're looking at the mechanism and you were to draw arrows for this mechanism, you would first show the heterolysis, right, the leaving group falling off, and then the carbocation intermediate, and then the nucleophile coming in. And this is the stage where you've lost stereochemistry. So if the nucleophile attacks from the bottom, then you would get this top product here. And if the nucleophile comes in from the top, then you would get this bottom product here. You can see what's going on in this picture in terms of HOMO and LUMO interactions. So the nucleophile, the HOMO of the nucleophile, remember HOMO stands for highest occupied molecular orbital, so that means it has electrons, is going to interact with the LUMO, the lowest unoccupied molecular orbital, of the carbocation intermediate. So with the LUMO here doesn't have electrons, the HOMO of the nucleophile has electrons, and these are going to interact nicely. And you can get attack here from the left side in the picture or on the right side. So either of these forms is allowed and the reaction can proceed. So here's another picture showing the attack on the carbocation intermediate by the nucleophile. So again, you can see here the nucleophile kind of coming in from this right side here, or back side. And then here is the nucleophile in that position. And then on this bottom picture, you can see the nucleophile coming in here from the left. And so it's ending up in the front. So you're getting a mixture of two products. Notice that in this case, you are seeing R and S because we have one stereocenter. So what would happen if you have two stereocenters? That's what you're seeing in this example here. So this is showing a situation where the leaving group fell off to form a carbocation intermediate, but there was another stereocenter present in the molecule. So what you're actually getting then as a mixture of products are going to be diastereomers because the other stereocenter is unaffected. And then we're getting a mixture of stereocenters at the center where the nucleophile came in. So if you have one stereocenter, as we saw in the previous slide, the products of the SN1 reaction are going to be enantiomers. And then if you have more than one stereocenter, you are going to have the products of the reaction be diastereomers. Let's look a little bit more at the SN2 reaction. Now the SN2 reaction, as I mentioned, you're going to get a single product. So what happens is the nucleophile is going to come in from the side opposite the leaving group, and you are going to have an inversion of stereochemistry at that position. So it's going to be flipped. In this case, the leaving group is on the front, so the nucleophile is going to come in from the back, and the reverse is actually true. So if we were to draw the leaving group in the back, then the nucleophile would come in from the front. you can see here a picture of what's happening. So here's a picture showing the backside attack of the nucleophile. So the leaving group is here, the chlorine, right? And the nucleophile can only come in from the side opposite of the chlorine. So it's coming in on this end, and because this happens all at once, it can't approach from the other face. At the same time, the leaving group leaves. This is going to create the transition state, which is shown here. Remember, the transition state in reaction coordinate diagram is that top of the hump, the kind of the camel hump there. And this is where you have partially formed bonds and partially broken bonds. And so you can see here that the carbon-chlorine bond is breaking and the carbon-iodine bond is forming. And then as the chlorine completely falls off, you see that the groups have been essentially inverted. And they have the little picture of the umbrella to show you what's happening here, and that the nucleophile is attacking kind of from the back side and kind of flipping the other groups a little bit. If we look at the way the orbitals interact, you can see, again, the nucleophile is going to have the electrons, right? These are going to come in into an empty orbital of our substrate here. And so this is where it's going to be a LUMO. Again, we have a HOMO of a nucleophile interacting with a LUMO. Okay, this is an empty orbital, and so this interaction is favored. But it's not going to work if this nucleophile wants to come in from the other way. So this is the back side. The front side is what we call forbidden, because you can see the way the LUMOs are situated here. We're not getting good overlap of the HOMO with the LUMO here. So we say that this part of this reaction is forbidden. So the HOMO of the nucleophile has to come in from the back in order to get good overlap. So it's kind of, again, one of the reasons why this is going to be preferred. There's also an electrostatic reason. So if we look at the electrostatic potential map, remember that the leaving group is usually going to be fairly electronegative, right? And so you're going to get some repulsion if an electron-rich nucleophile is trying to come in from that side. It's much more going to prefer coming in from the back side, right, where you're going to have some positive charge. You can kind of see on the electrostatic potential map here in blue. This is where the nucleophile is going to want to attack, not from the front side where there's also electron buildup.